Hello students, welcome to online maths classroom. Today we are going to start with our topic probability, and in it we will take its first subtopic, that is introduction to conditional probability. This is chapter 13 of class 12. So let us start with it. So first of all, we need to recapitulate few things about probability. So let us first of all take our basic difference between experimental probability versus theoretical probability. So what is theoretical probability? It is what expected to happen, right? Theoretical probability is what is expected to happen, and probability of the event is given by number of favorable outcomes divided by total number of possible outcomes. Now let us take an example of theoretical probability, that as when a coin is tossed, the probability of getting a head is half and the probability of getting a tail is also half, that is 1 by 2. Now what is experimental probability? This probability is found by repeating an experiment and observing the number of outcomes, right? So in this experimental probability, we'll repeat our desired experiment number of times, right, as we require, right? And then we will observe its outcome. Now here the probability of event will be the number of times the event occurs, right, divided by total number of tries. For example, if a coin is tossed 10 times, so a head is scored 7 times and a tail is scored 3 times, say this is the case. So what is the probability of getting the head? Now it is not half as it was there in theoretical probability. It is now you have multiple trials and the total means number of trials are 10, and had you got 7 times, so the probability of getting head is 7 by 10 now, and the probability of tail is now 3 by 10. Now what is simple probability? You know that probability is favorable outcome divided by total outcomes. See, for example, take a bag in which there are few red balls and few blue balls, right? So how to get the probability of red balls? It is the number of favorable cases, that is total red balls are 7, so 7, and the total balls are 12, so 7 divided by 12. Similarly, probability of blue balls is your 5 divided by 12. Now what is probability line? So probability line is your, like the terminologies like impossible, unlikely, your equally likely or certain outcomes, right? And we always know that the probability lies always between 0 and 1. Now impossible outcomes, like we take an example that picking out a red marble from a bag in which you cannot view any red marble is an impossible outcome. Unlikely outcomes are those like while throwing a die, right? Getting 1 in the first throw of die is an unlikely outcome, right? Means like even if we want to have 1 from a die, then it has the 1 in 6 chance of occurrence, right? So means very few chances of occurrence. Equally likely means where getting for example, getting head on tossing a coin, it has an equally likely outcome, right? Most likely outcome, we take the example like here that this is a pointer on the wheel is there, right? So the pointer will stop on the pink portion. It is the most likely outcome. Why? Because the maximum area of this your wheel is pink in color, right? So more favorable chance of occurrence or stopping of the pointer on the pink portion instead of the green portion. And certain outcome like taking out an orange marble from a can or from a box where the complete all the marbles, they are of orange color. So that is a certain outcome, because definitely you will get a orange marble out. Now what is conditional probability? Conditional probability we are going to start with, like we denote it as probability of A, and this dash is denoted by, this line indicates given, right? This line indicates given, or we can read it as A stroke B, or it is A by B, right? A under B, A by B, like this we can go for it. Now what happens? The event which is there at the top, means at the first you write, means like it is B by A, right? So B means this event, now it has yet to happen, right? That it may or may not occur, we require it or not, right? And A is the event which is down there by B, after this by sign is whatever is written, this event has already occurred, right? And it is definitely putting any condition for the happening of the event which we now desire to happen, right? Means probability of A by B means the probability of happening of A when B has already happened, right? We denote it by probability of A by B, and this is given by equal to probability of A intersection B divided by probability of B, or we can say that it is the ratio of probability of intersection of the events divided by the probability of event which has already happened, right? So the very essential condition here that lies is that probability of B should not be equal to 0, right? The event means some event would have already, means as if we say that the for fraction to exist, the denominator should not be equal to 0 by that way also. And since we are talking about the conditional probability, means that if some event must have happened earlier before getting our desired event, right? Now see, for example, a bag is there in which your 2 blue balls are there and 3 red balls are there. So total probability of getting now blue ball in this bag is 2 by 5, right? 2 blue balls is 2 by 5, right? Now if I take out one red ball out of it, now what happens? Now there are 2 blue balls and only 2 red balls left, because I have taken out this red ball and kept it aside, right? I have not, this is called the case of without replacement, means I am not replacing back. Now what happens? The chances of getting now blue ball out of this bag is 2 in 4. It is not 2 in 5. Similarly, if I remove a blue ball out of it, so here the blue ball will also be reduced. Now the probability of getting blue ball is 1 by 4. But what happens? Means means the drawing of this red or blue ball, they are putting conditions of on the second draw, right? Because what you are doing is first experiment, it was an open experiment, nothing, no earlier event has happened, or the earlier event has been taken out of it or has been removed out of it, right? So the chances of getting now blue ball, they are different, right? 2 in 4 and here it is 1 in 4. Right. Now what happens if for the second case, right, say if I say take out this red ball, this is the case, and then I before the second draw I replace this bag here in the first bag again. So again it will not alter or hinder the happening of the other event, because again the total number of balls will be 5 and probability of getting a blue ball again will be 2 in 5. But if I remove, then in that case the probabilities will be different, means they are conditioned now on the event that has earlier happened. So let us take your one question from your NCERT books, which is an like an example. An instructor has a question bank consisting of 300 easy true-false questions, 200 difficult true-false questions, 500 easy multiple choice questions, and 400 difficult multiple choice questions. If a question is selected at random from the question bank, what is the probability that it will be an easy question given that it is multiple choice question? So first of all, we need to understand that there are 2 events, right? What are the 2 events? One is that it will be an easy question. This is one event, given that it is a multiple choice question. There is one also event which is getting a multiple choice question, which has already occurred, right? So let us, whatever given here is, we will put it in the form of a table. And the table is this T, this is for true, false, this is MCQ, this is easy, this is difficult. In that way, it helps me to arrange all the data given in the question in an organized manner, right? So easy true, false questions means there are, from here I can take 300. So 300 from here, and the difficult true, false questions is 200. So there it is here 200. The this here 500 easy MCQs, right? So I'll put it here, and the 400 difficult MCQs. So they are here. So in total, the questions, number of questions are 1,400. 1,400. Now, what is the probability of, means the event which I desire is getting easy question, whereas this event multiple choice question has already happened. So means I need probability of easy by MCQ, means getting an easy when already MC questions are there, right? So what is the formula for this getting of this probability of A by B, or getting an event when one has already happened? It is the probability of the intersections divided by the probability of the event which has already occurred, right? Now what is the probability of easy and MCQ, right? So first of all, how many questions are there which are easy also and MCQ also? So easy MCQs are 500, right? So 500 out of the total, how many total questions are there? Like 5 plus 4 plus 3 plus 2, 100, means all hundreds, if I add up, they will make 1,400. So the probability is 500 divided by 1,400. And the probability of MCQ, so total MCQs are your this 500 plus 400, that is 900. So the probability of MCQ is 900 divided by 1,400. and this will get cancelled, and these 2 zeros will also get cancelled, and we'll get your 5 by 9. Right? Now there is another way of handling this question, right? Because if I'm not going to apply the formula, then also there is one very easy way of doing this question. And what that way is that since there is an event which has already occurred. What is that? Getting an MCQ question. Now what happens that my sample space, now the total means if we say probability, like the probability of happening of an event means number of favorable upon total cases. So now as one of the event has already happened, that is MCQ questions, so my total sample space means total possible outcomes now has restricted only to the MCQ questions, right? No true false, nothing about, because true false has no connection with it. So total questions, MCQ questions are this 500 plus 500 divided plus 900, 400, that is 900, right? So means my sample space total means total possible outcomes are thus restricted to 900, right? And out of these 900, what do I need? I need those easy MCQs. So see, out of these, how many favorable are there? Means how many easy MCQs are there? 500. So 500 means favorable upon total. So 500 divided by 900 will also give me the answer as 5 by 9. So this is another alternative way of handling this question. So let us take the case of a die. If you roll a fair die twice and observe the numbers that face up, find the probability that sum of numbers is 8, given that the first number is 3, right? So when a fair die is rolled twice, you know, the possible outcomes are your 36. Like we can take it as sample space 1, 1, 1, 2, so on, so up to 6, 6, right? So they are all different equally likely outcomes. And take the two events like A as the sum of numbers is 8 and B is the first number is 3. So sum of numbers is 8. The possible cases are this 2, 6, 6, 2, 3, 5, 5, 3 and 4, 4. Right? And the first number is 3 like 3, 1, 3, 2, 3, 3 and up to 3, 6. Right? Out of C, this C, how many intersection are there means sum of numbers is 8 and first number is 3. So only one favorable case is there, which is your, you can view from here is this 3 and 5. So this is the only common case for intersection, right? So what is the probability of individual probability of getting now A? That is your simple probability. If I calculate, that is your 5 cases are favorable and total are 36, so 5 by 36. This is the case of simple probability. And probability of B is your, how many cases are there? 6, so 6 by 36. And probability of intersection is your favorable is 1 and total is 36, so it is 1 by 36. Now I need to get that the sum of numbers is 8 given that first number is 3. That means I have to find the probability of event A when B has already occurred, right? So it is now the case of conditional probability. So probability of A under B is probability of A intersection B divided by probability of B, provided this you can see that probability of B is not equal to 0. So it is the probability of A is your this A intersection B is 1 by 36 and probability of B is 6 by 36. So the answer is 1 by 6. So as we discussed the other method here also. So in that way also we can go for this question, right? Since we have to which event has already happened, that the first number is 3, right? So instead of this 36 cases, my sample space now has restricted only to these 6 cases. Okay, why? Because I have to find the probability of getting sum of numbers 8 in connection when the first number is 3. First number is 3, right? So in that case means my total possible cases are now not 36. Actually they are now conditioned or restricted to these 6 cases, right? And out of these, which are favorable to A, means how many are there which are common with this A and B? Only one, that is 3, 5, right? So favorable is 1 and total is 6. So the probability is 1 by 6. So that's way that way you can also work with this. Now let us see the properties of conditional probability. Let E and F be two events of a sample space S of an experiment. Then property number 1 says the probability of S under F is equal to probability of F under F. This is equal to 1. Now by the definition of conditional probability, probability of S under F is probability of S intersection F divided by probability of F. Now S is the total sample space. You know what is common between a universal set and any other set is the set itself. So it becomes probability of F by probability of F, which is equal to 1, and probability of F is not equal to 0. Similarly, probability of F under F is your probability of F intersection F divided by probability of F, which is your probability of, again, what is common, its whole set is common, so probability of f divided by probability of f, that is 1. So we prove that probability of S under f is equal to probability of f under f is equal to 1. Second property is that if A and B are any two events of sample space S and f is an event of S such that probability of f not equal to 0, then probability of A union B under f is equal to probability of A under f plus probability of B under f minus probability of A intersection B under f. Right? So we can remember our addition rule of this probability, that is probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B, right? And since now the concept is of conditional probability, means some of the event is there which has already occurred. So what is that event? Like f has already occurred. So probability of A union B under f is your, again what you need to do is you have to put under f everywhere. So it's the same that addition rule, you have to put under f everywhere. So it becomes, instead of probability of A union B equal to probability of A plus probability of B minus probability of A intersection B, it is just like probability of this everything under f everywhere mentioned, right? So let us derive now this probability of A union B under f. Now let's apply the formula of conditional probability. So it becomes the intersection of both these, like a probability of A union B intersection f divided by probability of f, right, by the definition. And now open it by using distributive law here at the top, right? So it becomes A intersection f union B intersection f divided by probability of f. Now again operate it like apply addition rule, that probability of A union B can be written as probability of A plus probability of B minus probability of A intersection B divided by probability of f, right? Break the numerator, separate the terms, A intersection B under f, probability of B intersection f under f minus probability of A intersection B intersection f under f, right? So this, by the back definition of probability, conditional probability, it becomes probability of A under f plus probability of B under f minus probability of A intersection B under f, right? And in case of disjoint sets, what happens when the two sets are disjoint? You already know that their intersection is 0, right? So in that case, what will happen to this formula? That probability of this last term, probability of A intersection B under f, like it becomes, it is your probability of A intersection B, your intersection f, right? This divided by your probability of f, this will be your 0. This becomes your 0, right? Because in that case your sets are disjoint, so you will not get something common between all the three events. So this changes to 0. And probability of A union B under f, this formula reduces just to only these two terms, probability of A under f plus probability of B under f, in case of the sets are disjoint. Okay. The third property is that for if E and F are events for a sample space S of an experiment, then probability of E complement under F is 1 minus probability of E under F, right? So you know by property number 1, which we have done, that probability of S under F is your 1. So S, you can write it as probability of E complement union E complement, because E and E complement are disjoint sets, right? So nothing common is there. So probability of, you can write S as probability of E union E complement under F is 1. So now apply the formula for here again, because you know that we applied the previous property in which if the sets are disjoint, then the last case of intersection, that is rejected, and it just becomes probability of E under F plus probability of E complement under F equal to 1. And in that way you can calculate probability of E complement under F is 1 minus probability of E under F, or probability of E under F is your 1 minus probability of E complement under F. Now what is multiplication theorem on probability? That if say E and F are two events associated with the same sample space of an experiment, then we know by the definition of conditional probability, if we need to work out for probability of E under F, then it is probability of E intersection F divided by probability of F, provided probability of F is not equal to 0. And probability of F under E is probability of E intersection F divided by probability of E, where it is not equal to 0, right? So from here, if I cross multiply to get the value of probability of E intersection F, so from here it will become probability of F into probability of E under F, and from here it will become probability of E into probability of F under E. So let us understand the basic thing here is what is there, that probability of E intersection FC, it is like which event has already occurred? F has already occurred, right? So it is like, means probability of F means one, the event which has occurred, and into the probability of event. Now which event to occur? E, instead of which event has already occurred under F. So it is like probability of F into probability of E under F, or probability of E, because in this case your F has already occurred, right? So it will become your E under F, right? And here it will become E has already occurred in this case, so it will become probability of E, happening of E, and happening of F and E has already occurred. And in case of three events, what will happen? Like E, F, G are events of same sample space F, and suppose first E has happened, then F has happened, then G will happen. So it will be like probability of E into probability of now happening of F when E has happened, and then into probability of happening of G when your E and F both has happened, right? So what we have studied today is that if E and F are two events associated with the same sample space of a random experiment, then the conditional probability of event E under the condition that F has occurred, written as probability of E under F, is given by probability of E intersection F divided by probability of F, provided probability of F is not equal to 0. The properties of conditional probability, they say that E and F are two events associated with the same sample space as of an experiment, then probability of S under F is equal to probability of F under F is equal to 1, right? And probability, this is the second property, probability of A union B under F can be written as just an extension to the addition rule, right? Probability of A under F plus probability of B under F minus probability of A intersection B under F, and the last one is for complements, that probability of E complement under F is equal to 1 minus probability of E under F. And this is the multiplication theorem we have studied for 2 events and for 3 events, right? This is the way we can just apply the formula, right? Now these are the questions of your NCERT exercise, right? So in these questions where simple values are straight given, like probability of E F intersection is given, and you have to find probability of E under F and probability of F under E, so you can apply the direct formula and compute it, right? In question number 3, where you need to calculate, like A intersection B will come from your, as B under A is given, so when you will apply the formula for B under A, you can calculate it, this A intersection B. But for getting this probability of A union B, after getting probability of A intersection B, we need to apply the addition rule, right? So all the questions, like from question number 6 onwards, here the probabilities are not given, but you have to, events are given and you have to calculate first their respective probabilities. Then you have to understand that which event is yet to happen and which event has already occurred, and in that way you can go, right? So for example, this question number 13 we have already discussed. So see, we take the example of, say, question number 15. Consider the experiment of throwing a die. If a multiple of 3 comes up, throw the die again, and if any other number comes, toss a coin. Like, so this is the case of multiple event sample space, like the questions we did in our class +1, in which we framed the sample spaces, okay? And then the conditional probability of the event, the coin shows a tail. So this is my desired event, that the coin shows a tail, given that at least one die shows a 3, right? So means this event has already occurred. So you can frame the events, and then if this is, say, event A and this is B, you have to calculate probability of A under B, right? So I hope whatever is told to you, you will be able to solve this exercise on the basis of whatever we have learned. Thank you so much.